It's it's weird. It's still showing live, and now it's showing like what is? Oh, it's showing a bunch of tabs. Oh, there you go. It's moving now. Okay. Yeah, the user account controls are kind of tedious. Yeah, so I see both of us on my YouTube. Let's see.
Mike, okay, so now I'm back. Okay, sorry guys. Okay, guess I was muted. Okay. Can y'all hear me now?
Mike, okay, so
There we go.
now I'm back.
Okay, I can hear everything on my end on my
Okay.
YouTube channel. So
Okay, so I was blocked. Okay, I'm gonna stop recording this one and record maybe cause issues in next, please. Okay, now X.
yeah, there's always
Yeah, I don't
some
understand.
nonsense that we got to deal with.
Okay, yeah, I'm gonna just pop out chat. This one doesn't do it. Okay, it doesn't work. Okay, anyways, I'm gonna exit. And yeah, so I think it's fine. And why is this? Sorry about this. I'm gonna just make this above me. Okay, rotary matrix says it's good now, and I'm gonna go all the way to the end there. Just want to just check how I sound and so on. Okay, so I think everything's fine. Okay, there it is. Yeah, everything's fine. Okay, let's see. Oh, it doesn't work. Okay, anyways, I'm gonna exit. And yeah, so I think it's fine. All right, there it is. Okay, everything's fine. And yeah. All right, guys. Yeah, so we are live again, and so there is independent researcher. It says your name, Benefactor. All right, so that's epic stuff there. Okay, I'm getting a whole bunch of upvotes on my. All right, so here's the links to the notes. I put all your notes in here, and so what's cool is you know, on Google Gemini, so I have the workspace thing. I just asked it, make me a thumbnail, and it made a. Oh, I made it one for the other ones. But this one I use yours. But when I made it for those other articles. Okay, but anyways, I'll just read the stuff. Enough talking about stuff. So anyways, guys, so we are going live. So MES live stream 133, Beneficence TV. So Benefactor. I think that may or may not be his real name. You have to decide on yourself. Yeah, he discusses his. 1 second. This thing I gotta upload 3. Okay. Yeah, he discusses his recent breakthrough energy research. Yeah, so Benefactor from Beneficence TV joins the show again to discuss the latest in his ongoing research on energy recycling and wireless radiant energy. And again, you're on the Hive blockchain. Great to have you on there. And I actually got someone else today on it. So this was pretty interesting, the capitalism suppressive free energy one. That is pretty.
Yeah, we blew up on a couple of videos on the blockchain.
Yeah, so that's $3. So again, that's like, think about that. Like YouTube, it pays peanuts or zero. Almost most people get zero.
Right.
Yeah,
but
so,
more importantly, the information is getting out and the algorithm likes it. You know, like it's not like YouTube where, you know, just sharing reactionary shit. Like if the audience likes that stuff, it will get out. And that's what I like about the blockchain.
yeah.
We have better chance of getting the information out there. And yeah, no, like you're right.
Yeah.
Like there was like $3 on one video in like 1 day or a half a day it took.
Yeah.
And I ran the numbers in AI and it's like that's really good.
Yeah. And the other thing is it's all blockchain based. So it's like, because you know me and I have a big stake in Hive and a lot of people know me, if I share your thing or post, it's automatically the credibility of you just by because I share.
Yeah.
Because you know everyone's credibility for history. Twitter and so on,
Right.
you don't really know. You just know,
No,
yeah,
that's true.
yeah, like
That's true. And the blockchain, I'm able to share the information in text format and more easy and
video and
spread the
anything, yeah.
information. Yeah.
And
So I don't
yeah,
know. It's
yeah.
a better platform. I think
Well,
I need
yeah.
to
And the thing is,
start using it a little bit
I'm not
more.
sure if have you claimed your reward. You should have. It's right now. It's
Yes.
$2.75. Okay, when was the last
Yeah,
time you
yeah, I
claimed?
claimed everything. I made sure that I
No, well,
read up
you
on that,
claimed
but
no,
I do have a couple of questions.
no, but you claimed 22 days ago. Basically, every 7 days, the post gets paid. Like the new post gets paid. So,
So that was that was one of my questions is like, am I going to have to claim that like periodically, or I was under the impression it gets 7 days and that's it
no, no, on the
for
specific post, yeah, yeah.
monetization.
But you haven't posted, yeah, yeah, yeah. No, it's 7 days after the post, so you'll still have more to claim, because these ones
Oh,
were
okay. So
posted.
as long as I'm not posting, I don't have anything to claim.
No, yeah, but you posted this one 22 days ago, and the claim was 22 days ago. So you could this current one, this one, and this one. Anyways, we
Oh,
can
there
just
we go.
yeah. Okay, I can share. Do you want me to share my screen, or do you want to just watch the video on the YouTube?
No, you froze for a minute.
Okay, okay. Just because like
No, no, I don't want to.
yeah, are you able to
You
see
said
my
what?
screen or not? Like I'm just wondering what you're seeing.
Yeah, no, your image and sound froze for a minute though.
Yeah, I know, but just are you able to see my screen before we continue further,
Yeah,
or do you? Yeah, okay. So you're just watching on the YouTube and slightly delayed. It's like 5 seconds delay.
yeah.
Okay, no worries. All right. So anyways, yeah. So we'll just go straight into this, and yeah. It says people says froze brain accelerator froze for them too. Okay, that's interesting. Yeah, so I just want to make some random notes here. So I got this Chris Shack guy on the Hive blockchain. He's did a lot of occult mumbo jumbo stuff, and this other one. I want to ask you: have you heard about the Tesla Violet Ray machine?
No, I haven't.
Okay, so this was
The violet ray or violent
no,
ray?
no, Violet Ray. It's apparently uses
Violet ray.
on the purple bluish spectrum, where it's I think it's
I've
like
heard of the Tesla death ray.
yeah, but this one's like a life ray. Apparently has some healing properties, and it was selling a lot. You
Oh,
can buy
so
some
it's
vintage
like,
ones. Yeah, and that's like
I mean, there are certain researchers that I've, looked into that, utilize or claiming to utilize cold electricity, the negative component of the circuit with
mhm,
along with like plasma.
yeah.
So yeah, for that purpose, I don't know. It's interesting. I'd like to explore it in the future. I just know we can't really talk about it online. I don't think, YouTube's very sensitive to that kind of stuff.
It's all right. YouTube, as long as you don't go too overboard on medical claims. Yeah, because this one is apparently taken off the shelves in a lot of areas, but people still like use even vintage ones. They might even modern ones. They might use different names. This was apparently Nikola Tesla. He
Hmm.
introduced it in 1893. So it uses typically what you have is it's like you have a Tesla coil, I think, fit inside, and then you have a glass tube with some like noble gas, and then that
Yeah, yeah. So
ionizes
that's
it.
some
Yeah.
kind of glass to ionize it.
Yeah,
Yeah.
ionize, and you can put this on your shoulder and so on. This guy, I actually commented on
See,
him.
that's the
Yeah.
exact method. No, that's awesome because that's the exact method from the team that I did a presentation for the Water Tribe community a while ago, and there was a team that was presenting after me, and they talked about the same method using Tesla coils and making sure that only the negative electricity was getting out to the,
Hmm.
they use kind of like a light filled with gas, a bulb, but they used two bulbs. And what they did was they bridged them, kind of like completing a circuit. So say you had pain in your arm, you
Hmm.
would put one light on one end of the
Okay.
arm and one on the other, and it would complete the circuit, and the energy would go through the part that was in pain. So that's kind of the same idea, honestly. So that's interesting.
Yeah.
That's very interesting.
This one I want to test it out. And so this person he had some shoulder pain. And then he's trying it out. I actually commented on him. I was watching his videos before it came up, and he just all of a sudden he says he bought one because he kind of lives. He lives literally like off grid, off even. So he has everything on his bike. He just goes around, and again he lives off crypto and so on. And yes, I asked him to do a follow up. This was 22 days ago. He said he could feel something. It's noticeable. He feels better with it on. So We'll see how that is.
Interesting.
Yeah.
Yeah, I'm willing to test it out.
Yeah, I
I'm
want to
willing
get
to try it. I'll build
yeah.
something. I was already going to go exploring that way just because I have inflammation in my fingers, you know, for playing instruments so long, I assume, working with my hands. So
Yeah.
yeah, I'd like to explore that. That would be very helpful if I can get the inflammation down in my hands.
Yeah, for sure. And then lastly, before we get into the other one, is another random notes here. So the primer fields, like David Lapointe. I think you've covered him before. You know David Lapointe, the primer fields guy. Have you ever seen his?
No,
Oh,
I don't
really?
think I've,
Okay. Because
not that I recall.
you may have come
Maybe I don't remember.
yeah, may have come across without knowing it was David Lapointe. Because I think Ken Wheeler
Yeah,
has like whenever if you watch Ken Wheeler stuff, like recommended stuff's typically David Lapointe. He's pretty good, but he designed something, but he open sourced it so you can actually make it yourself. But if you want to buy from him, it's pretty expensive though. He has like these bowl-shaped magnetic arrays. It just permanent magnets, and it apparently has healing properties as well. And but it's
interesting.
pretty expensive. Okay, one of them is $700. Okay, $700. Oh, that's a 3-pack. Okay, that's pretty cheap actually,
I
relative to
mean,
what it used
if
to
it
be.
works, it works. You know,
Yeah,
like I just, you know, like I'd like to have
yeah,
something that's not a scam if
yeah.
it's that expensive.
But he open sources, so you can actually go 3D print and just get the magnets yourself. But I actually think there's something to this one because I contacted him. I wanted to see if I
See,
can get an
that's what
affiliate
gives me
point.
a little
Yeah,
bit, yeah, that gives me a little bit more ease knowing that he open
yeah,
sourced it and you can actually look at how it works. Because then I can break it down and say, oh, it's
yeah,
using only the negative components and
yeah.
it's safe. Because what the science team that I was watching a presentation at the Water Tribe community, they warned everybody not to get any hot energy. So
Okay.
your standard positive energy that you use out the wall and stuff like that, like
Yeah,
you only want the reactive component from your coil and nothing else, because it can be dangerous, they said.
yeah, yeah, for
So I
sure.
don't know anything about it, but you know, like that's just, I guess, a caveat there.
Yeah, but this is something I do want to like. I want to get a bunch of these. If someone has a 3D printer and wants to make it for me, because what's cool about this,
So
yeah,
it's probably putting out just the negative component in some way.
yeah,
I guarantee it.
yeah, because he actually goes. He has a he makes some similar ones where he can actually contain a plasma using these bullshit magnetic fields. So you could definitely check out his primer
Yeah.
fields, and then and then basically you can contain a plasma within there, and
I'm
it's
not really sure how it works, but I know
yeah.
that you have to have plasma in order for it to work.
No, he feeds in
From what
plasma in there. Yeah,
everything that I've
yeah,
read and
yeah,
everything that everybody's talked about, you know, these types of devices. Yeah, even Daniel Nunez was working with the plasma for that purpose.
yeah.
So that's very interesting.
No, it's just pretty interesting setup there. These bullshit. So I just want to get my hands on some of these. But yeah, he's and he goes through a lot of like his theory on the magnetic field based on when you check the poles and so on. But nonetheless, I just want to try this because I'm pretty good at promoting things if things work. But yeah, so we'll get on that.
Yeah, definitely. I mean, and if he's got the schematics, maybe it's something I can whip up in the lab here. Who knows?
Yeah,
You know.
yeah. So he used to have it patent like trademark, and then but then he released it I think last year. Basically saying I think it's open source. I think it is. Yeah. Okay. So 2019 they made open source. That's interesting. All right. So in 2019 they made it a completely open source and so on. Okay. No, actually no. That was I think no. It was open source, and then he said people were making them not the standards. And what was the thing he did? Oh, a huge change. Okay. So I think they did some AI setups.
Oh, so people were trying to rebuild it with his schematics, but not building it to spec exactly like he told everybody to. Like, that's a
Yeah.
problem with the Bedini motor. Like, people want to do their own modification or have their own idea and like, oh, just put this instead, and then it doesn't work. Or,
Hmm.
you know, like you get some kind of negative effect with that kind of device. I can imagine if you make the wrong move there, you know?
Yeah. Yeah. No, for sure. And now apparently he's working with ChatGPT to do some
So
other one with
that's
them. So that's pretty interesting.
that's probably smart though on
It is.
his
It is. It
part, you
is.
know.
It is because again, AI can like look up things that you overlook, even if it's like a mainstream thing, even if you
Yeah.
disagree with mainstream. Yeah, but it's like at least get it right. Because a lot of people they try to go against the mainstream, but they don't even know what the mainstream is actually saying. So, anyways, yes, that's pretty good stuff. And yeah, so let's continue on here. So I made your those I made two of the papers that you wrote into an article format on the Hive blockchain. I took a bunch of notes here, and then I also covered the Thomas. I watched the Thomas Bearden one, and again, it's just the synchronicity is mind-boggling. I literally did a
Hmm.
live stream last week on this Aronoff Bohm effect because of Thomas Bearden and so on. And so here's the setup here. This was Gemini AI thumbnail made. But yeah. All right. So basically, I want to ask. Yeah. So the thing is, for the stream, how do you want to go about it? Do you want to discuss what you've done so far, or how's your work going?
Yeah, so I have a couple of quick updates, and then I want to get into the paper that I've been writing regarding the potential method for calculating the instantaneous power
Mhm.
in partitioned energy systems. So I know that sounds like a lot, but it's not that hard to understand, honestly. I'm not a mathematician by any means. I used AI to help me with these equations, but the logic is pretty easy to follow. So when after my updates, I'll have you bring that on screen if you can, so everybody can follow along with the equations, and I'll just read it off on my desktop over there.
Okay, because I am sharing that article as we see. It's on screen right now, as you see.
Yeah, the potential. Okay, that's fine. So I just wanted to give you a
Yeah.
couple of quick updates before we get into that. So recently, I had some new theories for replicating the magnetic synchronicity and magnetic levitation experiments done by, Daniel Nunez, and the synchronicity experiment done by Jack Scholes. Um, because up until now, I haven't had any success in doing those experiments. Maybe synchronizing it for a couple of moments, but not permanently, like they do in the video, where they're taking it outside the coil for like 20 feet or more, and it's still spinning and reacting while the coil's off. That is something that I haven't, like, I have a couple of ideas, but we tested it with a very powerful 1000 watt class AB car amp that I got, because I thought maybe it was some kind of power factor in there involved. And we failed, but it told me a lot about how to proceed in that front. I think uh, in order to synchronize that magnet with the coil, and in order to get it to levitate in the center evenly, we have to have delicately placed wires, as seen in the version 3 PoE coil by First Stop Energies. So I have a coil frame made by Michel Morel. It is not
Mhm.
the First Stop Energies coil, but it is one that is open sourced by my lab partner and mentor, Michel. He designed this with the vortex-based mathematics engineering principles, and encoded with the 432 hertz frequency somehow. I have to get the full specs in order to understand how he did it. But those are the main details. So I'm going to be, in the next few months, I'm going to be working on a couple of new coils, because these coils are a good start. Like, even the lowest approximation of the work of Daniel Nunez or Jack Scholes, even the lowest approximation will yield some kind of positive effects regarding energy and magnetic field manipulation, right? But we need the delicately placed wires, I believe, in order to achieve that synchronicity and levitation effect, and possibly even maximize the energy output, the efficiency of the coil, which they're already really efficient. So it was a good start, but we're gonna take our time and design some new coils for the further testing. But regarding the mathematical framework for the synthetic AC model that I've been
Mhm.
developing, we're going to be going over that, and that's where I was talking about, the potential method for calculating the power in partitioned energy systems, and I'll explain all that. But last but not least, after that, I have a quick demonstration in the lab of a new circuit that I've been working on. Um, it's my own circuit, so I'm not really ready to release the full schematics just yet. I probably will open source it eventually, but it's proving to be really useful. Like, this one's proving to be way more versatile than the Lightning Thief that we've been working with, and it's possibly even more efficient. So what I mean by that versatility is The system I've developed here allows you to adjust the voltage to current ratio output on the fly, depending on the demand of your device. So say you have like a LED panel that requires a lot of voltage but little current, you can adjust that so it's only outputting the minimum amount of current that you need and the voltage. So you're essentially able to tune the efficiency on the fly very effectively, and it's able to run off a 9-volt battery. So it's really cool. I call it the impulse driver or the impulse resonator. It's just a working title. I'm not really sure what to officially call it yet, but it's able to resonate the coil at a lot of different frequencies, or at least utilize it. But the maximum resonance range you'll see as outputted as maximum voltage peak on your multimeter. So there are certain ranges that will peak, and then kind of you turn up the frequency and it'll kind of degrade a little bit, and then you'll get to the second harmonic of that and it'll peak again. And then as you get to that third harmonic, as you increase in frequency, you can lower the current while increasing. Well, obviously the current's going to lower the current demand, so you're effectively able to tune the device to what you need it for, and basically on the fly gauge the maximum efficiency of the system, which is really cool. And what it also allowed me to do was determine what was wrong with my Mark I coil, because I was having some inconsistencies regarding measuring, the resistance of it. You want to check the ohms, make sure the ohms are pretty close for each channel of the coil and all that. And if you're getting inconsistent results like I was, this thing, it turns out, because the coil fell at some point and smashed against the leads that I have, and they're not soldered, they're just twisted, and I have them taped up and separated, but one of them might have shorted, and that's what I'm thinking. But this device is able to tell me when that is shorted or not. So I can actually look at the power supply and see, oh, at this specific frequency with this duty cycle, the power supply should only be outputting 60 milliamps. And if it's outputting more than that, I know it's shorted. And I have to, like maybe go in there and readjust the wiring or something. But I was able to wiggle it and get it back on track. Sometimes thermal expansion also plays a role in that. When you're putting a lot of amps into that, the conductor is actually going to expand a little bit, and if they're not soldered together, they're just twisted like I have, you can get loose bits, and sometimes, things happen where they get shorted out, two channels that are supposed to be separated or whatever. So those are all mistakes that I'm learning from in regarding moving forward. And with this new coil, we're going to avoid most of those, hopefully, by measuring out each wire effectively, like almost like how Tesla did it. We're going to have each wire exactly the same length, and we're going to lay it down in the coil individually and wire it up as we go along, so we can, minimize all of those issues. So I think that's really cool. I don't know if you want to jump into the paper.
Yeah, I could do that. I just want to ask about that coil that you have, or that white frame you have there. So what's especially unique about this one? Because you said it's something.
So I'm not honestly sure the specs of it or how Michel engineered it, but he said he engineered it with the 432 hertz, or the number 432 in some way. I know it has 30 rings, so around each ring frame there's 30 rungs that you can put in, as opposed to, say, the PoE version 3 by Daniel Nunez of First One Stop Energies. He had 36 for his 3-channel coil. There's 30 here, so each channel, it's a 3-channel coil, each channel will have 10. Now I'm not really sure, other than that, it has the golden ratio. When you look at the outer to inner diameter of the coil, it's maintaining the golden ratio there. So you have a tighter inner diameter, which is not what we see in the Dragon 7 coil that we're working with. It's already really efficient, this coil, but this closing the inner diameter, making it tighter and closer to that golden ratio, it was always a theory of ours, Michelle and mine, that would increase the efficiency and, help guide the magnetic field to the shape that we want it.
Okay. And then later I have some questions about basically connecting your coil to Thomas Bearden's MEG, the motionless
Oh, the
energy.
Meg.
Just because just because there's something to this vector potential mumbo jumbo he's saying. And basically I want to see
I'm
how.
happy to
Yeah.
look into
Yeah.
it. To be honest, I don't know. I haven't dived into the Meg too much. I know just the surface level, but yeah,
Yeah.
we can definitely
No, it is.
look into that.
But like ultimately, what it is it's basically like your. So for your coil, the idea of it would be, can you map out where exactly the magnetic field is? Like if you were to draw it out, how does it look? Does it extend beyond the wires? Is it contained within? Where is the exact magnetic field?
So it depends on the configuration. You can have a configuration where it is condensed in the center, and you can have a configuration where it is expanding outward. It depends, but you
Okay.
can pick up the field. And I know Daniel Nunez did this with magnetic paper. I have it right here. I don't know if this is like, it's not big enough to do what we
Yeah, I
want to
have
do
that.
with it. This is tiny, but this is what he used. He set the coil down on top of it, or on either side or whatever, and he turned up the magnetic field. Like, he turned up the power a lot. He said, I believe in one of his notes, he said he had to turn up the power quite a bit to get that magnetic field imprinted on the paper, because I guess in certain configurations it just wants to condense in the center, but you can see the outline of the field. So
Yeah, yeah.
I have those pictures too. I'll send them to
Okay.
you if you
Yeah,
want.
yeah, for sure. And also the other part is like, because you have a magnetic probe, right? Basically, try to. It's like the key.
Yes.
Yeah, the key part about what Bearden is talking about is you try to find when the magnetic field is zero. So basically, whenever the magnetic field is zero, that's the
So
key part.
that's the weird thing about this, though. This thing could be spinning a magnet, and then I'll take the magnet out, and at certain frequencies and configurations, you'll put the probe in, and it won't pick up any field. And it's so weird. I don't know if this is just not sensitive enough. Maybe I need a more sensitive pole detector. But I do have a digital pole detector, and I just can't pick it up sometimes. And I'm wondering if it's there. It's just too sensitive for this thing to pick up, but I don't know. So yeah, that's a problem that I've had. But we can easily, test that by, trying to get more sensitive equipment. I
Yeah,
think
yeah. Is it this?
I don't know. It's like the coil is it's stubborn. It's weird. It doesn't do what you would think it does sometimes. And that's the whole point of, like, trying to develop a model around some of this,
Mhm.
these systems, is trying to understand, these weird effects. But yeah,
Yeah.
it's going to take some time, but I think we can do it. I think we can map it out.
No, it did definitely. I guess I'm starting to get a lot of it. I'm gonna show you just quickly because about that magnetic field mumbo
Mhm.
jumbo. So here's the Thomas Bearden one. So his setup is what they were trying to do is basically have the entire magnetic field within their coil. So everything outside of that, that's what's considered like magnetic vector potential, meaning the zero component. So whenever you have a condensed magnetic field, everything
Mhm.
else, it's not just zero. It still has some energetic effect where when he pulses the actual circuit. So see, I'll keep fast forwarding until you could
So
see.
that makes sense, though. I mean, if you think about it, the magnetic field isn't, it's either, it's not just going to stop in the midair unless some other force is pushing against it, right? And that must be, it's interacting maybe with
Yeah.
the aether in some way, and it's creating that second field. I don't know. I'm just
No, yeah, yeah,
spitballing
yeah.
here.
It's just but also when you pulse it, the change, so the change in the actual like that vector potential thing produces an electric field, and he's saying that's where all this excess energy is coming into the circuit. But then the issue
Right,
is,
because
yeah,
you're creating a
yeah,
dipole.
yeah. But then the issue he says with that is, well, you have all these coils and so on, but then the electric field comes in, that that pretty much fires up all the extra coils. So now you might have some subtractive components. So you need to measure everything
Yeah,
extremely detailed.
right.
Yeah.
And that the whole point of impulse technology is to get the magnetic field out before, and get it to collapse before the electric field
Hmm.
happens, right? So you want that to happen so fast, so you have the minimum amount of current. You don't want a lot of current, and
Yeah.
That's the whole point of the impulse, you know, to do it fast. And, you know, like to go back to, you know, it's a pulse is not an impulse. For those who don't know, you know, a pulse has a start and an end, you know, da, 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 that's a pulse. That's an impulse. That's instant, where the start and the end are overlapping. They're the same event. So you want that kind of event to happen real fast. So the electric field doesn't have a chance to really happen, right? And that was what Tom Bearden was saying, at least. So and with this impulse technology, that is, in my opinion, what's happening, especially with these types of vortex coils. You're just creating an impulse so fast that it doesn't give time for electricity to really happen. It's mostly magnetic field until you get to the load wherever component demands the current, and then it, you know, kind of manifests around that component.
Okay, interesting. Just because I thought when you watch his thing, he was talking about electric field coming in and using that. I'm not sure how.
I mean,
exactly
yeah,
does he
but
do that? Yeah, it's just a bit. I'm just trying to wrap my head around. But
I'm not really
yeah.
sure how the Meg worked, but the Meg
Yeah.
might not have been impulse technology. Like, it
Yeah,
worked with a magnet,
yeah.
so maybe it was a different type of phenomenon that he was working with. I don't
Yeah.
really know.
But what's interesting is so here's a setup here. Like here's that Aronoff Bohm effect that he's talking about. He actually said if you have this transformer, like I just iron like square or circle, whatnot. So you have the initial coil inside, you energize it. There's the output coil, but he's saying the entire magnetic field is within the actual that iron there. Outside of that is that linear non-curl vector potential. And then, but what he's interesting is that he says if you put a magnet inside and make it like, oh, touch this, and if you were to measure the magnetic field at the North Pole there, it would not register anything. So like all of the magnetic field gets sucked into this thing, even though you put a magnet inside, the magnet doesn't even register a magnetic field. That's what.
Yeah,
that
is interesting. I'm not really sure why that happens. There's maybe a cancellation of the fields or something. I don't know.
Well, yeah, that's the part where I think if there's some connection with your coil setup, well, just a Roland coil setup, is if it's somehow able to essentially suck up the magnetic field within a specific location, and so when you're pulsing it, because when you watch this very carefully, he's literally saying, and he's saying too, you pulse it. See this thing on the top left there? He says you would pulse it. And then that changes the actual vector potential. And then when you keep pulsing it, that change produces this electric field difference. Basically, whenever you have, it says here, E equals to the negative rate change of this vector potential moment jumbo. So I think, so there's a chance that the Roland coil setup you're doing, when you're pulsing it, that's the aspect that's driving from a mainstream perspective. What would be driving the energy?
I mean, it makes sense, because what we do know, and this is from direct observations from our lab experiment, we do know that in certain configurations it will pinch the pole of it will literally pinch close the North Pole of the field. So if it can manipulate the field like that, like, you know what I mean? Like, what else is it capable of that we don't know?
Yeah, for sure. And so if you can see the screen, it says here again the A part. This is actually my next week's live stream on Wednesdays. It's on the vector potentials. I just need to wrap my head around what is, because you can see it has this curl thingy. It's basically, I think the curls.
Do you have something up on screen? Because I don't see it.
No, it's on. No, because the thing is, are you sharing? So the question I'm asking is, because before, were you looking at the live stream thing, or do you want me to share my screen? I can share my screen. Which one do you prefer?
Oh, I can. If you have it on the live stream, I'll just look at the live stream. No, it's fine.
No, I know, but
I know the live stream's a little delayed.
No, that's what I'm saying. Is I was telling you beforehand. I'll just share my screen, and I know it.
Yeah, no, that's fine. I'm sorry. I must have misunderstood. But yeah, if you want to share it on the screen,
okay. So I will share this.
Delay. I get confused.
Yeah. Okay. I'll share that, and I'll bring this up, and then now I just want to test some stuff out, to see the audio works or not.
I can hear it.
It's actually an apple.
I don't think I've seen this one.
This is the one that you sent.
Is it? No, I don't. I don't remember this.
This is the MEG. How MEG?
Yeah, I didn't watch the full video. Let me see that because I didn't watch the end.
I just saw. Well, the end he's talking a lot about
Where's at the
the.
beginning?
This is beginning. The end he talks a lot about the logistics, and he said that he couldn't get any university to agree to a non. Circumvention agreement where they can't take over like the patent using their own patents and so on. Except then you found
Oh,
a
okay.
foreign one.
No, it's you know what it is? It's a lot of times I'll put it on and I'll listen to him and I'm not familiar, like I didn't see him drawing this and I was just listen, like
Yeah,
I'll
because
go
I
around
saw
the
this.
lab and I'll listen to
So I saw this just before the stream because I was making
so
some notes. So
I saw this picture. I'm like, I've never seen this drawing. It's because I was listening to this.
yeah, okay, yeah. So you definitely gotta watch this one. So I saw it in double speed just before the just.
No,
Before this.
play it. Yeah, because I
No,
want to see it again.
yeah. So notice what he's talking about. So the key aspect, even though he doesn't quite explain what magnetic vector potential is, but that is what everything is. Like if you go to Wikipedia, Aronoff. It's like once you think you know about magnetic field, then all of a sudden there's a random A field. Like so the Aronoff-Bohm effect.
Yeah,
Sometimes called
read that real quick because I'm not familiar with that. I hear him talk about it all the time, but I
yeah.
haven't really looked into it.
No, so it's a real effect. Again, he wrote a paper saying that the Russians or Soviets were able to like literally do cold explosions at a distance, and create like
Wow.
nuclear type explosions without the ionizing radiation. So you can actually do ridiculous things, and you could extract energy out. So you can make a cold explosion where instead of like let's say you're blowing stuff up, all energy goes out. It's the energy gets sucked in. Yeah, things get colder.
Yeah. It's an endothermic reaction.
Yes, endo. So
Wow.
it's taken in. So it says right here, it's Aronoff-Bohm effect, sometimes called the whatever effect, is a quantum mechanical phenomenon in which an electrically charged particle is affected by electromagnetic potential, despite being confined to a region in which the magnetic field and electric field are zero. And basically, it's saying that the wave function of a particle, blah blah blah. But essentially, what you have is this: if you
if it's saying that effect is happening
it's a legit
while
effect,
the magnetic and electric field are at zero, maybe that's how magnetic synchronicity works in the Roland coil. I don't know.
That's what
you turn off the
I'm
coil.
assuming. It's the same. It's the same class of stuff happening because if you see, here's an image right here.
Yeah.
So what you have here is the magnetic field pointing at me or into the page, and that's
Right.
because you have like a super. What they usually have is they have like a whisker, like a super thin like steel or just a super thin iron or whatever conductor, and they would have a magnetic field through it, right? But the entire magnetic field is contained within, and then everything outside of that is basically zero, but it still has this A potential. And if you were to send two electrons on top and bottom, exactly in phase, but on the outside, and if they enter here, there's a slight there's gonna be a slight interference change. So the actual wave phase gets shifted, whether you're up or bottom. So I made a open up my Telegram just to see it, and
that's interesting because my theory has been in order to do that synchronicity effect, we do have to phase change. We have to dual input the tone, and then we have to phase change it either 180 degrees or maybe 90 degrees.
Yeah, so I actually covered his 1984 report on this, but I wanted to get over Aronoff-Bohm effect. So here's in Veritasium, you know the Veritasium, the big YouTube channel? They did one on this as well. So basically, when you have a charged particle going in, so again, this red thing is the zero electric and zero magnetic field. So whenever you have a super, just everything's condensed into there. Outside of it, it can change, it can alter. See, this is the phase. When you have it off, the current off, and on, it slightly gets shifted. See the before and after. So you can actually change the actual phase of the electron beam without an electric or magnetic field, as long as it's you have a coherent source somewhere in there. Even though it doesn't go through the magnetic field, and you could definitely watch that. And you know Martin Fleischmann, right? The cold fusion guy.
Yes.
He actually even said, if we could actually play this, he said that the Aronoff-Bohm effect involves the change. Yeah, he basically says the importance of the Aronoff-Bohm effect, and he says that people haven't really studied it that much. I'm gonna play this. Here's a clip from way back.
Now, we are at the watershed, and there are some people who have sort of mentioned foundations, so I think the relation of the art of faith is not with you. I think that's going to be one of those fruitful acts in such a next section.
So he basically says the rejigging of the Aronoff-Bohm effect is going to be one of the most fruitful parts of research in this next century. So it's like, and then
start studying it seriously. Yeah.
Well,
I mean,
because I think that is, my opinion, what it's looking like. It's the connection between, a lot of people say ether, it's like vortex, Tesla stuff. A lot of woo-woo sounding stuff. Mainstream says a lot of technical things that nobody understands, not even them. They say
shit. It could be a big missing piece of the puzzle. Though,
I think that is essentially what it shows, because you can do things without a magnetic electric field. Like what can anyone do without an actual?
Yeah. See that sounds like spooky action at a distance.
It is, and then basically what he refers it to as like that's what he talks about, scalar waves. It's basically it's like a longitudinal push of the ether or space.
Okay.
Whereas the magnetic and electric field, you can think of them as the ripples or the vortex. So vortex would be and then the ripple could be electric field. But then he's saying the actual longitudinal push. So you have an ocean, you can move at a distance without sending a wave. So like imagine you had water and you push at one end. You just have the earth, you can actually shake it just by pushing forward. Instead of like up and down. So you can just listen to him discuss some of this, just because it's coming from his mouth. It's pretty interesting how he explains it, and just so you have an idea of what he's trying to grasp.
Doesn't have a curl.
Okay,
it's moving little B.
When he draws it out, he does it.
And here's why we can do it with the MEG, legitimately as proven in physics. In the MEG, suppose I have a toroid coil. A toroid is wound around like this in a circle, but it's wound all the way around it very tightly. And it closes back almost on itself. What happens in the toroidal coil is the magnetic field, the B field, is confined inside the coil. It can't escape outside. Normally the magnetic field spills out into space. We need to know two things. Magnetic field, any force field, is not a primary field of nature. The primary thing is always a potential. And it's called magnetic vector potential A. That's the name of it. Magnetic vector potential. Now magnetic vector potential is a weird beast. It's got two components, basically. One is swirling. It's a curl component. We would write that del cross A, and that is what we call the magnetic field B. And normally it hides the other component. It covers it where we don't see the other component. The other component is one that doesn't have a curl. Doesn't have a curl. It's moving straight. So the curl is zero. But it's still a real potential. If you take this toroidal coil, first of all, we had to pay to get that B field trapped. But it's been found by Aronoff and Bohm in 1959 that if I normally have a source of B field, I'll just draw a dot here that makes B field. It's actually a dipole. And here's the B field spreading out in space. I know that's a curled magnetic vector potential A that I'm looking at. And it's hiding this other component I can't see. It turns out if you take all that B field, all that curl component, and pull it back in and hold it in a little area, localized area, so that it doesn't spill out into space, you reveal outside there that hidden component.
That's probably what the Roland coil does.
That's what I'm thinking. And then when he watched the thing, he talked about pulsing it too. And then the key part is when he talks about the electric energy. I'll keep playing until like just maybe a minute, but it's pretty fascinating.
A potential.
Yeah, keep playing. I'm gonna have a quick smoke while I watch.
Okay, sounds good.
Isn't this interesting? If you localize the B field into a little small location instead of spreading through all space, you have all the B field energy you would have had through all space. You got that in your hand in this local space. But outside that, you've got a whole bunch of extra energy now in uncurled A potential form. Well, A potential is wonderful. In the curl form, it makes magnetic field. So if I've got magnetic field, I got all my curl component down here in this localization zone. And outside here, I have a new component of energy I didn't have used before in my immediate environment available. Isn't that interesting because it's easy to collect it? All you have to do is change it real fast. The time rate of change, dA dt, produces an E field in the opposite direction from where the A field was going, which direction it was heading.
Yeah,
it makes an E field.
And he talks about pulsing it. Yeah, so that's pretty much it. Then and
yeah,
but then he continues on when he talks about the Meg, where again when you localize everything. So here's the part where he discusses
material, making new transformers and all.
And he was talking about a specific material for this that he's.
We found a construction core out
some like nano crystalline setup there, but that's for
the shelf type of construction and nanocrystalline material. There's two or three types to do it.
See, that's the thing. Like I'm under the impression that at least for practical uses for like, you know, emergency purposes, we can extract energy from the vacuum in very simple ways. Yeah. Just using, and I think that the geometry of the coil helps facilitate that. Yeah. So I think, you know, the Meg and all that, they're really good components, but their tolerances are so tight, you know, like in the material you have to get is very specific. So but the science behind them, I'm sorry. I just wanted to.
No, you're right. No, you're right.
There's no point in having free energy if nobody has access to it. This is my main point. You know what I mean? Like, so.
Well, it is, but also like but like I understand from his perspective because like he was still asking for $9 million from a
investor. Well, in this phase he was experimenting. You know, honestly, I think if he was still alive, he probably would be experimenting with different geometries of coils, kind of like what Gerald's doing, not just the Roland coil, but other types of geometries as well. So, but yeah, that's an important first step in laying down all this physics, you know, and all the groundwork that he did. But no, it's important to understand this, and to be quite frank, I only understand a very small percentage of what he's teaching here. I'm still learning. You know, Tom Bearden he was very, very smart.
Mm-hmm. Yeah, just one second. People are saying that the stream ended same material for 10 minutes or something. Is it working on your phone? Can you double check?
Let me see my phone
or whatever you're using. Some people are saying that it's not working.
Some people are saying that it's not working.
Oh no, it is
working. It's working on my end for YouTube at least.
No, just someone said that. Okay, no, he just rewind. Okay, so he's back. Okay, so anyways, yeah. So
okay.
Yeah, going back into this part here. Okay, again, the fact that so Thomas Bearden, I understand his perspective in that, again, even 9 million, it seems a lot, right? But compared to the billions that Hot Fusion and all that get, it's like that's pretty cheap. But I definitely agree with you on. I think there's even cheaper ways. Like again, that's where the Roland coil, where you use geometry of the inwards vortex as opposed to a standard coil. So I think,
it's like a self oscillator. You know, like it's a regulator. If anything, it's easily able to achieve resonance. You know, like, and the thing is, you know, like this type of technology, like, with a low budget, might not be able to power a neighborhood, right? You might not be able to power your house, but you can definitely power your lights, charge your phone, stuff like that in an emergency. And it's easy to build, and it's cheap. So like if I sell it on my website, it's not going to be breaking the bank or anything. It's going to be really budget friendly. So like that's the whole idea, is to have easy access to some of this. That's not going to really disrupt the market either, because you don't want to ruffle feathers with the energy market.
No, I agree, and so my view is to have it where you can actually replace some things and just use it, and then that allows anyone to go build upon it. And if somebody does have $1 million, well, there's a working product. You could just go and and make it 10 times bigger and better. Yeah.
So. Exactly, and you know, like, we don't know, there could be civil war and the grid could go down. That's what, you know, like I'm trying to work towards an easy solution so people have something in case that happens, so they can, you know, charge their devices or have some basic lighting and heating, some kind of, you know, like basic necessities if the grid goes down, because you know, like our energy situation is not ideal. It's actually, we're in an energy crisis right now. So that's why I'm trying to rush to get this all out here, you know, to get these solutions.
And the thing that's worse than the grid going down is things gradually getting more expensive. I'd be like, oh my goodness.
Yeah, they're getting more expensive.
Like oil,
I mean, but if you could save on energy though.
Yeah, no, that's what I'm trying to say. That's why I'm saying like a lot of people scared of the grid. But that's like worst case. But like the current situation where like oil just doubles in price because of the Iran war, for example, like that's
right,
not helping. And then here they're adding a whole bunch of taxes to energy use and so on. So it's again, there's the government way, just tax and make you have to work harder to get less. All right, but I want to continue playing this part just because you mentioned the pulsing part, because and the reason I'm bringing it up because I think what you're doing is basically replicating the Meg using geometry alone, as opposed to
it could be. You might be right on that. I don't know. Let's watch and see what he says, because I'm always rewatching these and trying to make connections like that. So
definitely. I'll play this right here.
Transform a core, the material. There's two types to do it. That if I make a transform a core material here, I'll draw a simple one. This is just a diagram. It's not exactly the way we structured. Any source of magnetic field, for example, if I have an input coil here, like this, and I'm paying the input, all the magnetic field from this coil, all of it, is trapped in this core. It doesn't get out. There's no spillage out there into space. Interesting. How can I prove that? I put a permanent magnet very tightly across here. North pole here, south pole here. Got to have real good contact, no air gaps. Of this magnet, very powerful little magnet. It's right across the transformer core material. And then I take an instrument with a field probe to measure magnetic field B, and I put it right on, let's say, that north pole. My instrument measures no magnetic field, or almost zero. It's impossible to get total contact. You won't have the tiny air gap, so you will measure a tiny field. But essentially a zero magnetic field right on the surface of the magnet. Now that proves that all the magnetic field that normally spilled out of this magnet everywhere has got sucked into this core and is sitting there. When you localize the B field and expose around it that usually hidden, uncorrelated potential, that's called the Aronoff bomb effect. Aronoff was a student of bomb. Aronoff. Bomb was David Bomb, of course, as everybody's aware. And in 1959, they published a very formidable and fundamental paper in the Physical Review series pointing out this effect. When you localize this magnetic field in space outside this core, not in the core, outside the core, there appears this A potential. But it's the uncurled variety now. It's extra. I didn't pay for it. If you want to put it in proper gauge language, the Aronoff bomb effect gauge transforms the space outside the localization area, which means you see additional energy available there in space itself. That's rigorously proven in literature. Don't have to reprove 25,000 papers in literature. But it's not in electrical engineering, but it's in physics.
Yeah. I'm going to go right here, and then where he basically talks about pulsing it.
I put in, clever devil that we are, we put in pulses. Sharp rise time and sharp decay time. If I want to get a little bigger E field, I make a sharper rise time and a sharper decay time. I get an E field one direction one time and the other. And what happens is the space here. I can have as many coils wound on this core as I wish. Let's put an output coil on it. Just to say we got an output. And it looks like I got my drawing a little bit reversed. That's okay. There's an output. Over here I got a big load.
Yeah, and he also discusses that the input, you can have it like 300 to 500 COP, like the coefficient above whatever potential. Or
yes. So,
yeah.
I mean,
yeah.
if you want my opinion, I think just because we can't gauge the efficiency of these types of systems accurately with our standard methods, and we can go into this in my paper in a minute, but I think that some of these systems might be getting, you know, a little bit over unity, but we just can't see it or measure it. But to get something like a self-sustaining system where it has enough energy to, you know, cycle back and feed itself and sustain itself, that is a tolerance that the Meg crossed, right? That's the territory that not a lot of people or experimenters get into, but that's kind of like what we're trying to do with the Wattman reduction. You know, we're looking for that potential in a system in order to prove it, at least, you know, because Tom Bearden talked a lot about it. And I don't know, there might be some demonstrations of the Meg, but since the tolerances are so high and it's so hard to build, it's not easy to replicate, you know, whereas this experiment, I can show you how to build it. It's not that hard. And you can see the effects, you know, like if you don't believe them on the video, you can build it yourself type of thing. You know what I mean? So it's not out of reach.
Just 1 second. Somebody said that there was an echo in that video. I just want to see if I can fix it quickly. No, but no, okay. I agree with you on this. And we'll get to your paper on how to measure this stuff, because you had some very interesting points. Audio input. This is like ever since this is the only downside about the Max is just like the things aren't designed for it. Teams.
Yeah, it's okay. I mean, I use StreamYards, and sometimes that fucks up too.
Yeah, okay. Teams audio. Enable down mixing. I don't even know what that means. Okay. I'm gonna check this out. Does this work?
Power like oscillator, easy curve, whatever.
Okay.
So I just go right off the shelf.
They hear an echo, no, not you. Like, so what it was? Okay, now I think I fixed it now. What it was doing before was recording Teams, like coming to you and my desktop, and then so people would hear an echo. So I think it works now. So I know what to do now. So I'm gonna have to Teams deactivate all this stuff. Okay, where's the other one? Okay, this is Teams.
I'll have to say you have a hell of an audience. They're really on top of it. Like, you know, letting us know if the stream goes down and all that, or if there's any problems. You know, that's really helpful too on our end, because some people, don't say anything and we don't know.
Yeah, I tell you, let me know. This is messed up. Let me know. Oh, 1 second. No, I'll be there.
You want to go for a walk?
No, 1 second. I'll be back in a few just a minute. I need to sort something out. Again, I'm like babysitting my my handicapped brother. It was
it's no problem. Just play the Tom Bearden and we can watch him for a few minutes.
Okay, so let me know where do you want to play it from? It's
yeah, just play it right here. It's fine.
Okay, I'll play it right here, and I'll be back in a few minutes. I just gotta sort something out.
Well, what we really have that's significant, it's not a regular transformer. We have an extra energy input from the environment that we don't pay for. That's the key. Now let's draw the Meg diagram, and it turns out to be just like
the Roland coil axis is a transformer in a certain
I have my system called the Meg. I'm going to do the open loop. I'm putting in the operator input. I'm paying for that. Paying the power company. Or paying for a battery or something. But now, from the environment, I have this extra input of energy, and I'm going to put the bar over the A, and when I perturb it, it's going to be in dA, dt equal minus E. Instead of going out, it's going to come in. So now I have an extra input of energy into my system free from the environment. Just putting in the input I'm putting in. The other part comes along for free. I get that as an extra added attraction.
I'm back. Can you hear me? All right, I'm back. And
Yes.
all right, yeah. So we can keep playing out, but we can continue on to the next setup. I think we pretty much understand this part. So I put links to my. So again, it's just to me it was just mind-boggling how I covered the Thomas Bearden and Aronoff effect last week, and I didn't even know it was gonna happen this stream. So you can see my stream earlier, and I put a description. With the help of AI, just get it exactly as properly worded. So this is, yeah. So basically, this was my stream last week. So the Aronoff-Bohm effect is a quantum phenomenon in which a charged particle's wave function acquires a measurable phase shift when the particle travels through a region where the magnetic field is zero, but encloses a confined magnetic flux. In the standard magnetic version, two coherent charged particle beams pass along two different paths along the flux, and when they recombine, the resulting interference pattern is shifted by an amount determined by the enclosed magnetic field. And yeah, lastly, just to show you how like big this stuff is. So Thomas Bearden, so he has a patent from 2003, but he also has I think these are some rare photos. So here's Thomas Bearden as a young apparently he's a musician as well. I'm not sure if you know about this about him.
Oh, that's right. I thought I read something about that.
Yeah.
That's him?
Yeah, 1951. So it was part of the Rhythm Harmoniers. The guys, and I think John Hutchison's dad was also a musician. Have you heard about that? I don't know. Hutchison.
No, I haven't.
Yeah, so here's his mom and dad. His mom was like a model. So this is John Hutchison's mom. And there's his mom, some natives or something. And there's his mom, yeah, his model, and there's her with a horse, and I want to show the dad because so that was her, and then there's I think that's his dad, it might be, but here's this might be the grandpa and grandma, but here's I think this is his dad. He was a musician. I think he's the one in the center. So Ken Hutchison and his orchestra. He had an orchestra, Trans-Canada Network, featuring that. And there's a photo. Yeah, so this one here. I think this is John. I think this is John or his father. I forgot which one is which. It might be his father. So that's his mother. And I think this is that might be his mother. I'm trying to figure out where he is. Yeah, so his parents. This is John's dad, I think. I'm pretty sure this is John's dad. You can see how he looks like. It's pretty fascinating. All right. Yeah. Yeah. So yeah, I'll go back to the Bearden quickly. Bearden. I'm not sure if have you seen this report or no? This Thomas Bearden report. So this is the 1984 the Bohm-Aronoff effect, scalar interferometry and Soviet weaponization, just by Thomas Bearden. And apparently he hung out with John Bedini. Did you know that or no?
Tom Bearden, yeah, I knew that they collaborated to a certain extent.
Yeah, because he wrote it. Again, this is approved for release 2003. This is CIA declassified report, and they're talking about next level stuff. And I actually made on Google Gemini when you upload the PDF, you can turn it to a podcast, and it explains it to you as a person back and forth talking like we are. But it's
really that's cool.
But it's so good that I didn't. If you didn't know about it, you wouldn't even know. Like I'll play some of it, but it explains things so well. You could actually have a listen to this. But anyways, it's for the paper. But here's the
so
this is an AI podcast. If nobody told you, you may not have realized it's an AI. But they explain it in ways that normal people can listen. So this is it talks about the Aronoff-Bohm effect here. We could either play this as 4 minutes, or you want to talk about the other potential your paper. Which one? But I do want to. I'll just play a minute, then we can stop if you want.
in April 1984,
Just listen to this. This is pretty ridiculous.
commercial pilots flying off the coast of Japan saw something absolutely terrifying.
Yeah, a massive mushroom cloud, right?
Exactly, like 150 miles wide, shooting 60,000 feet into the air. It looked exactly like a nuclear detonation, but and this is the crazy part, there was no blinding flash, no heat. and absolutely zero radioactive fallout.
Which makes literally no sense under conventional physics.
Right. So today, for our exploration into the source material, we are diving into a 1984 report by T.E. Bearden, and he suggests this wasn't some weird volcano or a mystery bomb, but actually a demonstration of, well, phantom physics.
Yeah, he's talking about weaponizing potentials, which sells like a sci-fi ghost story. But he roots this in a real quantum discovery, the Bohr-Marinoff effect.
Which basically says space isn't empty, right? Like the old idea is that energy has to travel like a bullet from point A to point B.
Exactly. But to really understand Bearden's report, you have to flip your perspective. Mainstream physics treats these potentials as just convenient math shortcuts to calculate force fields.
I like to think of it like the ocean. Like classical physics only cares about the waves crashing on the surface. Right? Those are the electric and magnetic fields we can actually measure.
Right. But the Bohr-Marinoff effect implies the real power is deep sea pressure itself. Even if the surface is totally still.
So if the force field is zero, I mean, what exactly is moving the particles?
Well, that is where his concept of scalar electromagnetics comes in. Instead of the typical wiggling waves we use for radio light, these are longitudinal. They're non-Hertzian waves.
Like sound waves, maybe. Just rhythmically compressing and stretching the actual vacuum of space.
Yeah, exactly like that. Bearden actually calls it squeezing the massless charge of space-time.
Okay, but let me push back for a second here. Because if this was discovered back in 1959, why isn't this just standard high school physics? Like, are we just looking at a mathematical quirk that Bearden is blowing out of proportion?
Well, that is the multi-billion-dollar question. The report claims that if you accept potentials as the real engine, and force fields is just the exhaust, you could build something called a scalar interferometer.
And that's a device that crosses two invisible stellar beams.
Yes, you cross them at a distance to create this interference zone.
So
this guy's saying is an echo. Like I think I'm gonna reverse this one. Okay, I think I fixed it. Okay, well, this one.
Energy doesn't travel through the space between the transmitter and the target. It just emerges there.
Right, because the energy is transformed into space-time stress and then just reappears at the destination. By slightly shifting the phase of those intersecting beams, you literally create a source or a sink in the vacuum.
Oh, wow. So a sink would create what the report calls a cold explosion.
Exactly.
Yeah, that's the part.
You suck the heat out of a region, forcing the...
Yeah, so that's a cool thing. You can actually feed your paper in, and then it will make a podcast like this.
local energy to rush inward and vanish.
Okay. Yeah, this is using Google Gemini because I pay for the workspace for my email thingy. Like, so if I go to, for example, MES.fm/Hutchison, so it's in my I think I have. Okay, so here, so I put all the Hutchison hard drive. Like they gave me John and Nancy Hutchison gave me their hard drive, and so I paid for 5 terabytes just to store like 3 terabytes of theirs on Google. I was using Dropbox, but then they stopped made all the links I showed like stop working because it was getting too much volume. Too many people were viewing it. So I'm gonna go right here, just show you reports, for example. So you can go reports, and then so like here's an analysis patent and so on. I made another one on here's scalar weapons called patent. It was a patent one, I think. CIA. Where's the where did I put it? Okay, but I have one here on a patent. This is another. This is the Lockheed Martin room temperature laser. This was based on Aronoff Bohm effect as well. So if you go to Lockheed Martin, if I go back here, just to show you that they're all dealing with this stuff. So if you go to Lockheed Martin, where's Lockheed quickly? Lockheed Martin. Lockheed Martin, right here, 1 second. Yeah, so this is I thought I had that there just to show you, but so see this patent right here? This is a patent from Lockheed Martin, right? On generating coherent matter wave beams, and you could use it for cloaking and a whole lot of energy extraction and so on. And so they all references the Aronoff-Bohm effect. So this is Lockheed Martin, a recent. Yeah, and if you go to AB effect, it's like that's literally all there. It's all talking about AB effect. And what's interesting, yeah. 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 Yeah, and this is 2011 thingy there. So yeah, going back to that. So if you go here, well, yeah, they're creating the energy crisis. All right. So here's you can feed the whole pattern in, right? And then you can get the and then it does an overview. Same thing.
So, welcome to today's exploration into the source material. We have a pretty wild one today.
Oh yeah, it is definitely out there.
It's always the same. All the same two voices by default. But if you go here, and then you can just go click. It should be a create a yeah. It's this thing here. See this thing? Create an audio overview. You just I just press a button, and all of a sudden does it. And but it explains it in a way that it helps a lot. Understand that. It's again fascinating. And I did it with other setups too. Abraham sensor. I thought I had it in here. I'm just gonna throw that in there quickly. I'm gonna go to Bearden. Bearden report. Thomas Bearden. Cold explosion. Yeah, report show unfold. I'm gonna throw that in here just so we have that PDF. Okay, CIA. This is no, that is the PDF. Okay, that's a CIA one. So we have this one here. That's this one here. See this? And I just created an audio overview. That was the first time I did it, and I'm like absolutely fascinating how it can just do that. And again, I did it with here's Soviet AI generated, and it tells you all that.
So in April.
Yeah, but it just has a like it just makes it audio. I used Camtasia, my video editor, to make the transcript and so on. So, but anyway, so you can check that out. I think I have I'll just send you the link right now. Go back to Telegram. Okay, I'm gonna go back to this Bearden. Yeah, so up to you if you want to listen to the rest of it. It's absolutely it's one of the most remarkable setup there. And if you actually look at what they're saying, like in the actual report, so again they're talking about cold explosions and so on, and instantly they can instantly freeze every NATO soldier in that area. But he's blaming what's it called, Soviet Union. Yeah, yeah, but the yeah. Mm-hmm. Yeah, definitely. And but if you listen also like the example he uses as something that will happen in the future. He says particularly if monstrous cold explosions appeared without warning in densely populated regions of the U.S. In fact, one may argue that the Western military and civilian leaders would not even grasp what was being done to them or who was doing it. And he said, of course, the same scalar interferometry can be used to use in the quote produce energy mode, in which case it can jam or knock out almost all electrical equipment in the target zone, detonate explosive materials therein. Note that a massive electrical fireball, say several megatons, over New York City. Like what? out of all places. Yeah. 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 Mm-hmm. Yeah, oh, that'd be interesting. Yeah. Yeah, and again, he even calls it a new kind. Yeah, he calls it a new kind of directed energy weapon, and so on. And what's interesting is he even said there was a mushroom cloud off the Sea of Japan, and then 5 Boeing 747s flew through it, so there was no contamination. But why are they flying through that anyways? And he was talking about yeah, yeah. But here's the clip what I actually pieced together with the 9/11 one. But here's him. He was in a 1984, I think 1985 or CNN report as well, talking about cold explosions. But here's actually him talking about it in 1984.
Bearden believes that these satellite photographs are of mysterious non-nuclear explosions near an uninhabited island in the East Siberian Sea, and that they are discharges from an RF weapon that uses interceptors.
Okay, so now the guy's saying your audio's gone. I don't understand what's happening here. Okay, so your audio is gone. Okay, Teams is gone. I don't understand what's happening in this world. Teams. Can you here just speak right now? Just test. Just speak.
Hello.
Okay.
Testing.
It should be
1, 2.
working. This guy says your guest audio is out now. How's it out? It says it's working. I don't.
Interesting. I'll check it.
I don't understand every single time there's an issue. I to this day I do not know why there's an issue. It should be working. Let's see. I'm gonna go all the way here to the end.
I mean, I'm picking it up on YouTube on my end. So
Oh, like your audio,
weird.
like you're talking.
Yeah, everything's working fine.
Okay. Oh, it's frozen up.
It could just be frozen. Yeah, maybe it's frozen.
No, I think just for him. I think yours is fine then. Okay.
Yeah, his internet connection.
Yeah. Okay. So yours is fine. Okay. So I'm pretty sure it's working because that never happened. That specific thing never happened before. Okay. I'm gonna go back to where was I?
Well, I don't know how much time do you have. What time do we have?
Okay, so we have 2:19. Yeah, we should. I have any time, but usually my max, I try to max it at the 3 p.m. mark. But yeah, so up to you. What's your time? Should we go over your specific things? I got.
Yeah, because I don't want to like run out of time. If
Yeah, again, yeah, and
it takes it might take, I don't know, like maybe 30 minutes to go over it.
Yeah, so we'll go over this
Maybe a
one
little
here,
more.
and because you wanted my input on the math stuff. Well, if ChatGPT or I think you used ChatGPT. Which one did you use?
I used Google.
Oh, Google
but
Gemini. Okay, Gemini.
I did double check it with all their various AIs like DeepSeek and a couple of others I can't remember.
Yeah, and
but I double checked the work with various AI models and I have it critique it and try to find any flaws. But so far everything checks out. I just want a human being who knows mathematics to go over it, and that's why I sent it to you.
Yeah, I was going over. It looked decent there. One question first I have is, I didn't know why when you had the equations, why they're a bit blurry. Like, were they small? Because
yeah, no, I had to copy and paste them. They don't really copy and paste, and so I clipped them with.
No, I know. But what you could do is, well, I don't know, maybe zoom in because I just do the same thing. What I actually did was I took your equation here. Because what you could do with AI, this is probably my favorite use of AI. If you, but I use Grok mainly. So you could go to Grok, and you could just tell it, turn this equation into a nice latex form. That's what they're called. Latex is the rendering thingy. So because your image wasn't that clear, so then so this is how I upscaled it. Equation form, nice equation, latex equation form. Just render it, man. Just render it. Okay, why? Okay, there it is. Yeah, see this right here? Okay, I think he's gone. Or so we lost Ben. But anyway, yeah. I just want to show what you could do with this equation setup here. This was your equation? How it's blurry? Oh, can you hear me?
Yeah, no, that's fine. I just
no,
I don't use Grok personally.
No, but you could use a Gemini, whatever. You just ask it. You could upload the image and just say turn it into nice form, and now you could zoom in. So I can zoom in and then take a high definition screenshot. So again, it's just a side note. But anyway, so I made it here. So we can discuss this part here. So yeah, I realized this is how they actually do the root mean squared setup. So you're so like you understand the root mean squared pretty well, I assume.
Yes. I just want to give the audience a little bit of introduction. So for those who aren't aware of the synthetic AC model that I've been developing, it's proven to be a good start for bridging the gap between, say, the abstract concepts of vortex-based math, Tesla's impulse technology, and Tom Bearden's asymmetric regauging principles. It's a good start at bridging those with mainstream electrical engineering practices so we can actually utilize on the workbench. However, a part of that theory has always been an extension of what others have said for decades, and that is that this type of energy cannot be accurately measured with our standard tools. So in order to understand how to develop a workaround for this issue, studying these types of systems, I had to ask myself why. And specifically, why is it this type of energy cannot be accurately measured with standard methods? So, since the engineers will be demanding a mathematical framework to go along with the synthetic AC model, this is that attempt at creating that mathematical framework. So to start, though, we have to understand this fundamental flaw in mainstream thinking. So mainstream electrical engineering treats everything as a closed system governed by the laws of equilibrium thermodynamics. But this completely ignores the fact that a separate set of laws called non-equilibrium thermodynamics governs open systems interacting with environmental gradients. Now, a couple of examples of this, to put things in perspective, you can imagine equilibrium thermodynamics in a closed system viewed as, say, stagnant water in a sealed pot, right? There's uniform temperature and there's zero net flow. Now, we contrast this with something like non-equilibrium thermodynamics in an open system, which can be thought of as a persistent whirlpool that is maintained continuously by a drainage gradient. So the variable there is the geometry that is maintaining that persistent whirlpool. So that's kind of like the context of what we mean by an environmental gradient. It doesn't have to be physical. It could be something interacting with the magnetic field in some way. But before diving into the new power calculations, we do have to fundamentally change how we look at electrical circuits. Now, to understand the mathematics of an open non-equilibrium system, we have to understand three foundational concepts. The first one is the loop fallacy. Conventional electronics teaches us that current must flow in a complete closed loop from battery's terminal through the load and back to the opposing terminal. Now, while this is true for moving electron charge carriers, energy itself does not travel inside the wire. Remember, energy travels mostly through the space around the wire in an electromagnetic field envelope called the Poynting vector. Now, when you use specialized geometry, such as the Abha coil, which is a Roland coil variant, use special geometry coupled with rapid time asymmetric switching, you can physically partition these field vectors using something as simple as a high-speed diode. The forward energy and the backward collapse do not have to fight each other in the same wire. They can be geometrically guided along entire separate pathways while still being coupled via a field bridge. Remember, diodes, they block current, but they still allow for field interaction. So the second fundamental concept that we have to wrap our heads around goes back to the root of the synthetic AC model, which is reverse symmetry versus asymmetric sequencing. This is differentiating between a true alternating current signal and a synthetically created alternating current signal. Now, a true AC signal is reversal of the same energy. You're reversing the polarity of that same energy. You can imagine this as a closed pipe filled with water. A piston pushes the water forward and then pulls it back along the exact same path. That water is simply sloshing back and forth in place. Now, because the fluid is constantly reversing direction, it's actually fighting its own momentum, creating friction and heat while it does so. Every push forward is entirely undone by the backward pull. So you're losing some as you alternate that current. As efficient as it is in electronics, synthetic AC is proving to be more efficient because it is the sequencing of two or more bidirectional pulses. Now, you can imagine this as two separate people standing on opposite sides of a room, taking turns firing ping pong balls into a central zone, one after another. It might look like an alternating waveform on a standard meter, but in reality, it's a choreographed sequence of independent time asymmetric events. These two waves might look identical on a root mean square or RMS meter when they're averaged out. However, as we peek behind the curtain, we realize a stark truth. These two waveforms are not the same. True AC is not the same as synthetically created alternating current. So why do we categorize them as being the same? The synthetic AC model aims to correct this inherent contradiction, but we need to formulate a new mathematical framework in order to determine the efficiency of these systems if we're going to get anywhere with the engineers. A new methodology needs to be formed from this thesis. So this is my attempt at a potential method for calculating the instantaneous power potential of nonlinear systems that utilize synthetic alternating current. Now, the third concept is the RMS blind spot, and this is what we're talking about when we're talking about standard meters. Standard digital multimeters or averaging oscilloscopes do not look at reality in real time. They use mathematical smoothing tool called root mean square, or RMS. RMS acts like a statistical blender. It takes sharp, high energy spikes, such as the reactive negative 168 volts output from my coil, and smooths it out over time into a gentle artificial average. If you have a true, so in reality, that negative 168 volts could be peaking at, say, 200, maybe 300 volts, but it's smoothing it out. So, and as a result, we have an artificial average. You know, it's important for gauging certain systems and for utilizing for measuring in certain ways of our system, but it is not useful for utilizing the for gauging the actual coefficient of performance in a system that utilizes synthetic AC, like an open system, such as the modified Joule thief we have with the Roland coil. So, if you have a true sine wave, compare that with a nonlinear pulse-driven synthetic wave, their integrated averages might yield the exact same RMS voltages. However, how they release energy is different. How they interact with the environment can be very different, and how they perform work under load can also be radically different from one another. So thus is the need for this new synthetic AC classification. And I have to remind people, at its core, synthetic AC and the model of synthetic AC is at its core a taxonomy correction, right? It's a classification correction. So let's just jump into it. The mathematics that follow will completely abandon the artificial averaging of root mean square. Instead, we'll look at the instantaneous power integration over time measured in absolute units of work, joules. Now, by calculating the forward path and the backward recovery path, the collapse from the coil, by calculating them both as independent thermodynamic events in joules, we should be able to accurately track how a geometry-dependent open system successfully harvests energy from environmental gradients. So from this, we can extrapolate how much energy, if any, and that's a big if any, is being extracted from the surrounding vacuum. So we have a method to calculate if the system is getting a COP greater than 1, whereas before, these methods would just render that unseen. Even if you're getting a little extra power, say you're getting 120%, right? You're getting a COP of 1.2. You know, it's not enough to self-sustain itself. It's maybe enough not even to notice that it's getting above 100%. Especially if you're averaging out everything and you can't actually see the power yield of that impulse that's happening. So if the energy is being transferred mostly through that impulse event, we should be able to see it with this method. Now, it could yield a COP less than 1, who knows? But if there is any energy being harvested from the vacuum for free, this method will undoubtedly calculate it. Because again, remember, we're getting 10 plus volts output. We're putting in 12 volts from a battery. We're getting only 10 plus volts output from our coil, but negative 168 volts, and they have different paths. The positive energy, the 10 volts, is going to the load without any obvious return route back to the battery. It's just dissipating in there. While the negative energy is creating that bridge back to the battery. However, it is getting a negative 168 volts back to that battery. And that's the average, by the way. That's not the actual calculation using this method. So that could be inaccurate, but it is getting a lot of power back to the battery, which is, it makes sense why it lasts, 15 plus hours on 12.2 watt hours of energy compared to a standard off-the-shelf inverter, which, operates maybe 80% efficient and it's only lasting 3 hours. That's a big difference. So that kind of inconsistency in engaging, so the meters are telling me it's not getting over unity, but this, is obviously running for a long period of time. And it's only at a duty cycle of 50-50, which means like it's not mostly off. It's only off for half the time. So even if we account for the duty cycle, it just doesn't account for all that extra. So this is a method that we can utilize going forward. Now, this is where you have the graphic up. The standard way to calculate efficiency is the root mean square. And it's using this calculation right here. But because the root mean square and squaring operations in general, RMS voltages do not obey linear addition. So, for example, if you have two independent orthogonal AC waveforms, say two 5 volt RMS waveforms, adding them together does not equal 10 volts RMS. Their combined effective voltage is calculated via the vector sum, which is the square root of the sum of squares, which is that.
Yeah, it's right here. Yeah.
Yeah. Yes. So,
Oh, you're frozen.
The COP equation. It froze?
No, for a second. Yeah, now you're back. Okay.
Yeah. But the correct methodology, in my opinion, to fix the COP equation is to properly account for all partitioned energy events. Now, in normal systems, you're not partitioning the energy. You're kind of either abandoning that extra energy or you're not utilizing it effectively, right? The negative return from the collapse from the coil, it's either being underutilized or just discarded. Whereas in this system, we're utilizing it with the forward and we're timing it correctly where it's a dance and it's creating that perfect alternating current between those two oscillations. So we need to account for all partitioned energy events. We have a forward energy event and a backwards energy event, and they're not equal. They're not picking up as equal on the meters, and they're in fact picking up as being partitioned during the closing end of the loop of our circuit. So to properly account for all these partitioned energy events and prove the COP could be greater than 1, we must completely abandon the concept of averaging RMS and focus strictly on instantaneous power integration over time in joules. So remember, energy is work measured in joules, and power is the rate of energy transfer measured in watts. We must measure the input and output energies independently by calculating the exact area under the respective power curves. So first, we have to define our time domains. These domains in my system, the Lightning Thief at least, there's 2 domains and they're time asymmetric, meaning you're getting a bigger reaction than you're putting in. And they're not even. We have T1 and T2 in our equation. So we're going to separate them. T1 is the duration of the active forward excitation pulse. So you're measuring the forward pulse alone. T2 is the duration of the asymmetric field collapse, the radiant recovery event. So that's the backward energy. And then capital T is the total cycle time, T1 plus T2, or however domains you have. You might have more than 1 bidirectional or more than 2 bidirectional pulses that you can utilize. You might have 4. You might have a true AC signal with a synthetically alternating signal superimposed on top of it. So that also needs to be accounted for as well in systems like these. So true instantaneous input energy, because the backward pulse dynamically alters the battery source local scalar potential, you cannot use averaging input current. For this, we must integrate the instantaneous product of input voltage and input current. So the equation for this is, the input equation is true input energy equals the integral from 0 to capital T of input voltage times input current with respect to overall time.
Yeah, so
you have that. Okay, you got that right there. Awesome.
Yeah, so like
so again, this is
have you dealt with integrals?
It took me a little time to learn how to actually understand and integrate, but what are your thoughts on this so far?
Yeah, it's pretty straightforward. So like integral, that's just the area under the curve. Like you understand
okay, that's the area under the curve.
That's all the integral is just the area under the curve. What integral does is it makes them infinitely small rectangles, and then and it sums it up. And okay, there's one thing like this whole integral thing. It seems all fancy and so on, but all of that is based on the what's called the fundamental theorem of calculus, which is basically it summarizes that the integral, like the area under the curve, involves the anti-derivative. So like, you know what a derivative is of a function?
Yes.
Yeah,
I'm familiar with derivatives.
Yeah, the integral is the anti-derivative, and I think.
Oh, okay, that makes sense.
So if I go here, I'll do a quick one here just to show you, because I just posted it yesterday, and I have a little overview of the fundamental theorem of calculus. If I go to MES Science, I'm I posted my video yesterday on Kepler's 3 laws of planetary motion. I just click here. I don't know why it's so slow now. Yeah, I'm just gonna click here and then go to fundamental. So I put it from my screenshot. So essentially, the fundamental theorem, like it is part of the fundamental theorem of calculus. Like this integral function, it just equals to like this g of x is just it's such that the derivative of g of the derivative of g of x is equal to the function inside. So it's like, and that is basically just the area there, and you could see, yeah. So you can see where's this thingy? I think it's an area. That's how you derive it. Okay, but yeah, we'll get to. I thought I had a good overview. I'm gonna see if I had a good thumbnail for these. Yeah, and essentially this is what happens. You just literally sum a bunch of rectangles from my videos 10 years ago. But anyways, let's go back. So what matters in your equation is just that is this part accurate, which is this voltage times current. That's energy. Is that so what is voltage?
Yes, so we're capturing the high speed we're capturing the high speed signal in and specifically we're capturing traces of the instantaneous, the impulse, right? We're using input voltage and input current directly at the source terminal. So you're just capturing the voltage and the input directly with a high speed oscilloscope at the input terminals of the source battery. So you're basically you're capturing them, and it's not an unconventional way to capture that part of the
Oh no, that's fine.
those numbers.
No, but what I was asking is the voltage. So voltage times current. What is that in mainstream physics? Voltage times current.
So that gives you your watts. So voltage times
power,
current gives your overall power.
And then your power, your watts is basically energy per time or per distance. I think. Oh, that's Ohm's law. So I just want to get.
It's over.
Yeah, this Ohm's law. Voltage.
I believe it's over time because it's how energy transfers.
It's over time. Yeah.
Right. So there's a time factor in there. But what we're doing here is we're just capturing these two numbers with the high-speed oscilloscope, and we're multiplying them to find the instantaneous power, and in order to integrate them over the exact time that we captured with our inputs from before, the T1 and T2.
No. So this is correct. So V times I, then because you said that it was basically energy per time, right?
I believe so, yeah.
And then this is a DT over there that basically cancels that out. What you're gonna have is an area. Yeah, it's gonna be an area under this curve. Yeah, that's pretty much. I think that's. Then you have to multiply it by time.
And that's what we're looking for. Yeah.
Yeah, because what you're gonna be graphing out is the power, and then you're gonna be multiplying it by the area is gonna be multiplied by time. So you're gonna have an energy. Yeah. So the total is gonna be energy. And I always thought this is what actually I thought this was what they do.
Honestly, yeah, I mean they might do it in some instances, but it's very rare if they do. And to be honest, in order to capture effectively the real numbers of a high speed impulse like that, you need a really, really high speed oscilloscope. And thank God I have a really, really, really probably the best one you can get on Amazon for the average consumer. It's really, really high speed. You need an average oscilloscope that you buy, even an expensive one isn't really going to pick this up. You need a really off the charts oscilloscope to pick up these impulses accurately. And that's why, thank God, I got one, and I budgeted for it because I had some money come in for the channel and all that. So I made it a priority to get the best oscilloscope, the fastest, the highest speed one. And thank God I did, because I wouldn't have been able to pick up the synthetic AC waveform, the resonant pulse waveform that we pick up on the oscilloscope. It's just, you don't see it in other oscilloscopes. It's not there.
Yeah. Okay. No, so I want to wrap my head. So in the root mean squared, you're just getting the voltage, and you're saying the oscilloscopes, they're able to get that, but you have these pulses. Would it? So even if you're using root mean squared, they'll still be inaccurate regardless of the smoothing out, because of the instantaneous matter of the pulsing. Is that true or no? Like is the oscilloscope?
Yeah, anytime you're trying to measure an impulse with RMS, it's going to average it out, you know. So
No,
it's not going
I'm
to
saying
give you
besides
full
the no, besides the actual RMS smoothing out, like the oscilloscopes that do use this, because you said it was hard to calculate and it's hard to determine the voltage. To just
Yeah,
measure
but
it?
there's different settings. There's different
Okay,
settings
so
you
on
can
there.
use
Okay.
on the oscilloscope.
Oh,
Yeah,
so,
different
yeah.
high-speed oscilloscopes. If you get a high-speed current
Okay.
probe, for instance,
Yeah.
yeah, and then you can use the oscilloscope to capture that time factor. So
No, this is
I'm not
I guess-
exactly sure. There's a method to do it. I haven't read up on it quite fully yet, but I know there's a method to do it with my oscilloscope. I just it's a matter of trying to get the methodology correct, you know, where I'm measuring the energy with the probes and all that. And honestly, I don't have a high speed current probe. I need to order one of those. I don't think it came one came with my oscilloscope. I have to double check, but I'm pretty sure I have to get one of those in order to, you know, do this fully. But yeah, the RMS is just going to obscure anything. I mean, it's important to gauge the RMS. Don't get me wrong. You need the RMS to actually tune the system with a rodent coil in the lightning thief, because you need to be able to see where the maximum resonance is. You know, you need to, like, as you tune with the potentiometer in that system, you're looking for the maximum increase in voltage, and the digital multimeter is going to average it out, but it's going to still show you where that maximum region is overall.
Okay, that's good. No, wait, maximum like individual voltage, it still gives you that? You said or region, what do you mean?
Right. So for instance, you hook up the multimeter and you're reading the voltage output of the lightning thief, which is just a modified Joule thief circuit with the rodent coil hooked up. So you twist the potentiometer, which is connected to the base, and adjust the frequency. You know, you find the resonant frequency and it starts exciting this process that increases the voltage output of your system. So you put 10 volts in, you get 100 volts out, for instance.
Okay. No, I think I think I get it. And here I just quickly just ask Rock, visualize that curve there. So that's what it's just an area under the curve. So like if you have your power function, if you just graph it out, and then the area under it, that's just the total energy. So UN.
Right. And now
all.
for the output, we have to track the two partitioned output energies separately. This is the tricky part that a lot of people miss because they don't think about it this way. You know, most people just think about energy as energy, and in some systems, you know, I believe because it's my opinion, it's my theory that this is happening in my system. I've seen it, or I've seen evidence of it. So because our system partitions energy in two distinct spatial pathways, right? We have the forward going to the load without any obvious return path back to the battery, or at the very least, very minimal return path. And then we have the backward recovery terminal going, the backward recovery component going to the negative terminal of the battery. So we must compute their energies individually in joules. And then once we do that, we can actually add the joules together and fit them into the rest of the final equation. So joules can be added linearly, I found out, whereas RMS values cannot, as we discussed earlier. Now, we have two parts to this next equation. We have the forward work, and then we have the backward work. And they're similar, but so the forward work equals the integral from 0 to T1, which is our time domain 1, right, from before. Integral from 0 to T1 of load voltage times load current with respect to time. And then the backward component is calculated as backward work equals the integral from T1 to capital T of recovery voltage times recovery current with respect to time. Now, I just realized that might be T2. I don't know. What do you think? Do you think this is a mistake? Do you think this should be T2 for the backward component? Because
it says T right here. For the backward, you want T2. But one thing I wanted before we get to that, so this part, so you have the U in. I just wanted to wrap my head around. So this is the energy in of like just coming from the battery or the socket or wherever you're putting energy in.
Right, you're measuring right at the battery's terminal.
Okay, this battery's terminal. And then this forward one, So you're separating them into two. Again, they're all pulsed. This one's being pulsed. Like I just wanted to understand where's the pulsing coming in. See, this is
So the source. So you can imagine once the system's in resonance, the battery is being pulsed on the return. But you can imagine the energy going from the source battery to the circuit, through the coil, and the circuit is pulsing.
Okay, the
right?
circuit's
the circuit
being pulsed.
is switching on, and it's pulse. Yes, and
But
it's pulsing.
this one is
exciting the coil.
But this one's continuous though. So this input energy is just the continuous from the battery, and then
Exactly.
Okay,
Yes.
so that's continuous, and now you're pulsing here, and this is the thing about pulsing, because pulsing, when you integrate, it's an area under the curve. Wouldn't it be a summation?
I'm not sure. See, this is the exact question that I would pose to you. Like, would that be a better route to do? I'm not sure. I'm not a mathematician. I used AI to help me with this. I know the logics make sense.
No, I
and
agree.
I know
Just
the
because,
methodology is there, but
yeah, just because pulsing, when you have this this right here, the equation, you're not going to have typically a pulse one unless you can have one function like that. This is something I'll need to see the actual numbers. You might need to just sum it up somehow, but it's the same idea. Integrating a pulsing because they're super like rapid. Yeah. So this one I want to wrap my head. So now you're gonna pulse. Energies comes in, and this is forward work. This one is going to the load, and then backward goes to the battery. Is that or did I get it right?
right. So when we measure the output, when we have a high-speed diode on the positive rail, remember the diode, it blocks current, but it doesn't block the field interactions. So the fields between the forward and the backward fields are interacting still past that diode, but that is blocking the current from returning the positive current, and it's allowing the negative current to go through to the battery's negative terminal, which is kind of like a sinkhole. It wants to go there. It doesn't want to go through the load, which it has the choice of going through the load or the battery, but the load is high impedance. It's kind of like climbing uphill going to the load, whereas the battery's a sinkhole, right? For the negative energy, at least. And then the positive energy is being blocked. So that really doesn't have a logical way to go back to the battery. So it's my working theory that this field bridge is creating that connection back, closing the loop. But when we probe the output, say probe the voltage on the positive and negative output rails, we get negative 168 volts and only 10 positive volts, which doesn't make any sense unless we're dealing with an asymmetric time event, right? And they're partitioned, and they clearly are, because we've actually done the testing, hooked up the ground to the ground outlet in the building, right? So I grounded the system out totally just to make sure that negative potential was there in the system. And we still picked up negative 160. So it wasn't kind of like a fluke or a measurement error or something. That's actually negative 168 potential going to the battery, and only 10 positive volts, which we can clearly see as a 40-watt panel only lighting up about as bright as 10 watts would get you, or 10 volts would get you, right? So the logic is there. We just need a mathematical framework for calculating that. And this is saying we need to calculate the forward pulse to the load, and then calculate the negative return to the battery in a specific way, and using the instantaneous calculations, right? And then we can calculate those, turn them into joules, add the joules, and then fit them into our overall COP equation, where we divide by the total input.
Yeah, I think it's pretty straightforward. The only thing I need to just see is when you actually have the probing the values.
Right, exactly, and that's going to tell us a lot, and maybe there might need to be adjustments, like you said, like a summation instead. So
yeah, just because and the thing is, like, what's your oscilloscope can integrate, or wouldn't it just be summing? How would it know what's it's actually?
I'm not sure. I'd have to do some research on that, but I know my oscilloscope is top of the line, so whatever like really advanced feature is out there, it probably can do.
Okay. Yeah, I think it's pretty straightforward, because there's no energy's not going anywhere else. Like the schematic you had. So you had the modified joule thief high-speed diode. Energy is either going forward path to the resistor load or backward to the negative. And then basically, because mainstream physics assumes closed source, there's no external energy coming in or out. And then basically, when you sum these up, they should be equal or less than the energy in. There's no other
Right, exactly. So, we plug those into the final coefficient of performance equation, which is the COP for synthetic AC equals forward work plus backward work divided by the true input energy result.
Yeah, and one thing I want to see if you can, when you're testing this, is see if you could run the same calculation for just a normal circuit and then compare it with RMS. See if a
Right,
normal
exactly. That's a good experiment to do. We want to compare the regular efficiency results, how we would gauge it normally with this new result. And who knows, maybe the COP is like 99%, or 99.9%. Maybe it's under COP of, or maybe it's under unity. But at the very least, this gives us a method to calculate if there is anything extra. You know what I mean? Like, so
yeah.
I just want to be clear. Like, I'm not claiming over unity. I think this is a good method for calculating that if it's there, though.
No, I agree. But again, the thing I was saying is not only just compare with RMS on your Joule Thief, but just take a normal actual like non-pulse DC, just a normal AC, and then try to calculate the actual V times I and then integrate, and see if that lines up with the RMS average.
Yes, we'll have to do a lot of different testing and
just on a normal one
to compare, to different.
Yeah.
And I want to take different tests of different systems. Like I got this new circuit I'm working with. I haven't taken any readings of the oscilloscope yet, but I've been really itching to, because I literally just got this thing working Friday. So yesterday when I got my pulse width modulator unit, I was able to get this work because, I had a couple ideas on how I couldn't get the circuit working for like a week. I'm like, okay, I probably need this, or this. And I finally got it working. And I was like, holy shit, it's working and it's working great. And I can't wait to show you guys actually.
That's actually, I never used Gemini like this before. I'm going to just ask it, make an audio overview of this article of your
no, tell it to do that and the synthetic AC model because I'm curious.
I thought this was this. I thought this was a synthetic. I got the wrong link. Oh, this is the this is the other one.
The math so this is the math framework that goes along with the synthetic AC model paper, but I think you should feed it both of them because I'm curious to see how it reads it. I would love to hear that.
Yeah, and also in this thing, I made a bunch of notes about when I was reading your paper, time symmetry is not enough to characterize energy flow.
Right.
Yeah, this is.
I mean, to be clear, I could be wrong on some things. Like if there's some corrections that need to be made, obviously, I'm not going to be sitting there being like a jerk, like, no, that's not. Like I bring this to the public because I need answers to certain things that I don't have answers for. I might be wrong on some things. Some things might need to be adjusted, but like at the end of the day, there are certain core fundamental logical. There's certain arguments or certain arguments that I make that can't really be debated, like the classification error. That's clear. That's not like debatable. That we do that. We lump all those different types of AC into one category. Why do we do that? We don't do that with anything else in science. If we have a pressure wave under the ocean and a surface wave on looking down on the surface of the water, but we don't classify them as similar or the same. They have different designations.
No, that's one thing I learned from your papers there. And then lastly here, just because I'm gonna have to go in like literally a few minutes. I'm getting like hassled in the background.
Oh no, it's okay.
This is I wanted to show the audience this part.
This synthetic AC waveform is so cool. So it's a bunch of nested harmonics, and then you zoom out, and it forms a perfect smooth sine wave, like you would expect with the interaction between.
But you also have. But is this how it's supposed to be? Like an actual sine
wave?
No,
that is not a traditional sine
wave.
No,
that's what I mean. Like if you included in there a traditional sine wave, just for the lay people, like I haven't.
That is a good idea. I will accept that. That is a good critique. I will probably have to do that.
But I'm starting to visualize it. So if you zoom in, you also see you call this the 0 point point where it goes up and down. This
I mean I called it that because I didn't know what else to call it. It might not be, but
Yeah.
it's my idea like
Yeah.
that could be the 0 point, the convergence between the two counter rotating fields. I don't know.
Yeah, and the other part I want to ask is, well, just if you can specify the zoom level in it in the scope, like this one. So this is zoomed out, right? This is zoomed out. This is using a different geometry, so I understand that.
Yes, that's using the pancake coil instead.
Yeah.
That's this one right here.
Yeah.
It's the same circuit, only a different coil.
Okay, that's cool. Okay. Yeah, that's the yeah. So that's yeah, I see it. That's amazing. Yeah, so that one's there, and then well, basically, I'm trying to get at is so we understand that now. This one here, what's the level of zoom on this 0 point setup?
So that's all the way that I can zoom in.
Oh, and then this is zoomed out a bit. Okay, so this is.
Yeah, so if you hit default on the oscilloscope, it goes to the standard scale
Like
that
this
you
one.
would be viewing any signal at.
Right.
That's the middle point where you see all the nested harmonics.
Yeah, no. So basically, this is the one that you're. No, the default scale would be just this giant sine wave.
No, the default is the middle one.
Oh,
the top one, yeah, the nested
Oh,
harmonics.
and then to zoom in. Okay, this is the middle one. So you got to zoom in. You get to
Yes.
this. Yeah, so that's part. Just so we can
And if you zoom in on the other geometry, or the other coil with the other the different geometry, the bell one,
yeah.
that convergence, it's kind of there, but the sideband activity, how it's real thick, it's not thick on that one. It's very thin. There's like almost no energetic activity. It's almost like a line or a squiggly, you know, like, so it's different.
Yeah, I know, that's great stuff. And one thing again, I learned a whole lot because like I said, I'm forcing myself to learn electrical and just a whole bunch of science stuff. And this is how I force myself. And so basically, I'm not sure much time. Yeah, there's not much time. Do you have enough time to show an experiment, or say that for another day?
Yeah.
Okay.
Yeah, I mean, I have it all set up. All I need to do is turn it on. I'm not going to disclose the circuit quite yet, so I won't show the thing too up close, but I will show you guys it working.
So
I have it hooked up to the 40-watt panel.
So I'm gonna stop sharing, and then basically you can show it. Then just run it, and then I'm gonna have to head out after this. So so I stopped sharing my screen, so no more screen sharing, and that was just some nitty gritty. And then if you can explain to us again in a simplified way, so we know mainly input output is what I like what's the efficiency and so on. It should be obvious, like what's coming in, what's coming out. But I do understand the pulsing.
What I'm doing right now is I'm seeing how long it lasts on a 12-volt battery under specific conditions, comparing it to different systems. So that's the only way that I can really gauge the efficiency at this point, since I don't have a high-speed current probe. But this is proving to be really efficient, and specifically, you can adjust it. So the main problem, and I love the lightning thief. It's a great simple solution for off-the-grid lighting, right?
Yeah.
But it has a fundamental flaw, and that is it has one resonance, and that's it, right? You turn a potentiometer, and nothing happens, and it has one little zone that it will excite the coil, and that's because it has a feedback loop. It's self-oscillating, meaning, and this is the problem why I couldn't pick up the damage to my coil, is because it will dynamically adjust to its natural resonance. So if there's a short in there, it's going to adjust the frequency and just naturally adjust the frequency, and you won't even know because it'll work, right? It just might be a little less efficient or whatever, and you might not even notice. But with this new circuit, we can gauge that. We can actually adjust the coil's efficiency much more efficient, or much more precisely. So we have a pulse width modulator that I'm doing that with. So we turn this on, and as you can see, lighting my panel pretty bright.
Yeah, that's super bright. That's amazing.
But I can also adjust the frequency and duty cycle, which in turn adjusts the voltage to current ratio. So if I want to increase the brightness or decrease it, I can on the fly, right? Depending on my device's demand.
Yeah, can you explain the duty cycle a bit? It was a new thing I was looking up after when I read in your paper.
The duty cycle is how much time is your signal on compared to off.
Okay.
So if you have a 50-50, if you have a 50% duty cycle, it's on half the time and off half the time.
Okay.
If you have a 90% duty cycle, it's on 90% of the time and off 10% of the time.
Yeah.
So by adjusting this, though, we can adjust the frequency as well. As you can see, we can adjust the brightness. It's getting a little bit more current, and you can see this is our that's 60 volts right there extra that it's lighting up. Right?
Yeah.
That's a neon. That's a gas in there, so it's exciting it very easily. It's very low current required.
Yeah.
So we can see there's a lot of extra voltage coming out. That's a 12-volt battery, by the way. And that's a 40-watt panel. That's probably about 50% or maybe 25% bright. Right? It's way brighter than the Lightning Thief. The Lightning Thief only got maybe 12 to 13% bright, and you have to adjust the resistor on the base to do that. This, you can do it dynamically.
Okay, that's cool. I was gonna ask, like, can you make it set up so that it powers your computer or your laptop, or
I'm working on it, man. I'm working
on
it.
Or charging a phone.
The phone is going to be the next small step, because ideally what I want to do, and this was always phase 3 of my testing with these systems, is at the very least try to see if there's any way to make a self-running scooter, or maybe just a very efficient scooter that you have to charge less, than a traditional one. I don't know. But maybe bringing some of these ideas into a scooter so I can save on gas.
Yeah, that's cool, because you got that light all running up there. Another thing is if there a way you can just have like some sort of like it connects to like an outlet, like a multiple head outlet setup, so that you could just plug and play different amounts of energy, like for example different loads, different lights, and then if you have enough, you add a phone as well, because you basically create your own outlet.
That's exactly what I mean. Yeah. So with this type of energy, it's different because we have to rectify it into the type of energy that your phone would take, right? So your phone's not going to be charging off of an impulse from the negative side. It's going to be charging with hot energy. We got to rectify that in some way, but we can convert it. And the idea is that this is a resonant system. So whatever you hook up to it is going to dynamically change the frequency and adjust, kind of like water leveling out, and kind of sit to like a natural good efficiency in the system. It's a self-regulator like that. The rodent coil is just very efficient in that way. So whatever we hook up to it, as long as we found a way to do that, charge a phone, I guarantee you, if we found a way to do that, and we might be able to,
that'd be a big one. Yeah, charging a phone.
Yeah, it's not really going to affect the system in any way efficiency wise. It's going to probably get the same efficiency.
Okay, so and then what kind of loads would it be increased efficiency? Like this light setup is more efficient than just plugging it into the wall.
So right now, plugging it into by the time you get energy out the wall, it's like 40% of what it was. But
no, that's what I mean. Yeah. Basically, because you're saying that a phone's not going to be that efficient, but wouldn't it still be better than plugging into the outlet, or like in terms of energy consumption?
No, I'm saying if we find out a way to charge the phone using this method, I don't think it's going to affect the efficiency of the system. I think it's going to be able to charge your phone pretty efficiently.
Oh no, that's
if we find a way to
So basically, I also compare it to the mainstream. So would it be much more efficient than the actual socket that I use in the house? Like that'd be just would that be much more?
So I haven't actually gauged the efficiency of this yet, but I mean, at the very least, it is going to be more efficient than the Lightning Thief, I believe, because I mean, you're able to adjust the current dynamically. So if we're able to do that, we can fine tune it way more. And also, it has an indicator when I hook up to the power supply if the channel is shorting, and that creates enormous inefficiency too. So that's a big problem if I'm trying to gauge the efficiency of the coil and I don't know the wire is shorted. It's going to give me, like, for instance, if I hook it up to this the power supply, I can have it at 13 kilohertz and 50% duty cycle, and without it shorting, when it's working properly, it will only draw 60 milliamps from the power supply to do what it needs to do and light this thing. But if it's shorting, it'll draw over an amp. So that's the difference here. Like it's a very big difference in just think about traditional coils. that the traditional coils can't do this to begin with, like not with a 1-to-1 ratio. You have to have a different number of windings on the second coil in order to have any kind of step up of voltage. So that is very unusual to begin with. So that tells us we're dealing with something a little bit different in terms of electromagnetic coils.
Yeah, no, this is fascinating stuff. And I'll be testing my Tesla coil thing set up soon. Basically every other Wednesday morning I focus on it, and I was looking through some of the safety setups, but I'll be on there. Okay.
Nice.
Somebody says, did you guys see they claim Amy is alive? Hidden a lawsuit. Sally evidently is seeking damages. I think it might be to you, this person. Jenny Kofi 1443. I don't know if you didn't know her. Somebody said
Amy Eskridge.
Well, the person commenting is Jenny Coffee 1443. She says, "Did you guys see that that they claim Amy is alive?"
Huh. Interesting.
And then,
no, I didn't see that.
And who's Sally? Sally is evidently seeking damages. There's a lawsuit or something. All right. But yeah, I'm gonna have to head out before I'm like babysitting my brother right now. Okay, it is just excluded. Yes, I don't know who is what that means. All right, and I was gonna say yeah, just we need to figure out how you get the efficiency and so on. Like basically, we need to finalize the numbers. Like, is this over Unity? Is this under Unity? Okay. I don't know what this person is commenting. It's just his partner. It is. I have no idea what this person on the chat's saying. All right.
What?
No, someone's in the chat saying stuff. I don't know what's going on. I don't know if it's to you, because I don't know this person. Claim Amy is alive. Who's Amy? X tweeted. Partner X. What is she saying? It just twittered. It just. Okay, she just tweeted. Okay. Yeah, but anyways, I'm gonna be having to go. Yeah, thanks for this and another thing. You know how you had that other article that you were working on, but you said it wasn't good enough to post yet.
Yeah, there's some. That's probably not going to be out for a while, because I have to test a couple of things on that, and it's going to take a bit. But,
no, but another thing about the Hive blockchain is, like on that Peaked website, if you just on the drafts, it saves it anywhere you go, so you can even without publishing, you'll still be able to save it on your account. So you could work on it there, and then once you're ready to publish, you can publish whenever. That's what I do. Like my articles, okay. I have a whole bunch of drafts that I never
to be honest. There are large sections of that paper that I need to rewrite just based on a couple of theories I had were wrong, and I need to change my perspective in that specific paper at least. That's why I asked you not to publish it, and I appreciate that. I just like I
agree.
I had a feeling.
I'm just saying that you could
wrote it down.
No, I'm saying you could work on the drafts. Yeah. You could work on the drafts on Peaked, and then you just save the draft. You don't need to publish. And then you could publish whenever you want. So it's kind of like instead of using Google and then having to convert everything to Hive, you just work with Hive and just say, like, I'll share my screen one time, but then I'm gonna have to get out of here. So share Windows quickly. If I go, whoops, I shared the wrong one. Okay, I'm gonna go back here just to show you. Because again, I pretty much use Hive instead of I try to replace everything, so that I don't need to use any other ones. Introduction. So okay, so my brother's calling. Just to illustrate what I do here. So here's my screen. If I go to drafts, if I make it slower. If I go to drafts, so view drafts. So I can like work on these and then publish them later. So it's like I had some working here and so on. So and these save anywhere you go. And this is just a draft, hasn't been published yet. So you can just go, yeah, cancel. I don't want to save it. So like, for example, and then once you're ready to go, you can publish. Like this one is published, but you can work on the draft. Like I was working on it for a while. It wasn't just all in one go. So that's kind of what I mean. You could, so you can do, all your drafts get saved. So like this one here is one I'm going to be writing an article on. This person that saw UFO in 9/11. And so anyways, you get what I'm saying. It's like you can work your paper that you work on Google, it's right here, work on here, because I want to get more people using the Hive blockchain, as opposed to, well, pretty much anything else. It's just next level. Anyways, I'm gonna stop sharing, and yeah, I'll show you the person commenting. This is the person commenting. Person saying, it's
Okay.
just, did you guys see they claim Amy is alive hidden in the lawsuit? Is apparently some tweet. Oh, Eskridge, yes, it is Eskridge. So Amy Eskridge, someone's tweeting that it is alive, and Eskridge is posting. I don't know who Eskridge is.
Really
Yeah, so that's an interesting thing. Anyways,
interesting. Yeah.
all right, but anyways, I'm gonna have to head out. I'm gonna ask the audience any. Then I'll close the stream, and then we could talk privately for a few seconds before I gotta go. Anything else you wanna?
Okay.
Anything else you need from the audience?
Yeah, so if anybody wants to visit my channel or help support my research, you can visit my channel or my Patreon. So we have memberships on the YouTube and Patreon. So just go to patreon.com/BeneficenceTV. It's linked in my YouTube as well, Beneficence TV.
Yeah, and I put a link to all your stuff in the notes and in the description of the video. This live stream description has your setup too. So you go to I'll put a link to this right to them. So you guys follow Beneficence TV. Whoops, and yeah, and again we'll be doing this again periodically on and off until we need to, because again, like you said, we're in an energy crisis, but I think it's a scripted energy crisis where it's like things.
I mean, yeah,
unless we have to, but regardless, it's the same thing. Yeah, but regardless, it's the same result.
Yeah, to be honest though, yeah, like whatever it is,
it's the same
we
result.
need solutions. Yeah, and I think we're on a really good. We have a really good foundation of bringing at least some things to like to people who need them. So hopefully we can advance that energy research and provide a device that charges a phone or something.
Yeah, and then build from there, like you said, the electric bike and so on. All right. Anyways, I'm gonna tell these people thanks for joining, guys. I'll just say that. Thanks for joining, everybody. I'm gonna end this stream. I'm gonna stop recording.
Yeah. Thanks, everybody.
Yeah. Adios, peeps. I'm gonna stop recording. Okay, I'll go stop recording.